Good afternoon. My name is Peter Lawrie, and I'll be talking about microservices, but within the context of applications that are designed for high performance. I'm a Java developer myself, and I do consulting, and I've worked with hedge funds and investment banks for about 8 years in the low latency space, and about 23 years working in IT. I'm quite active on Stack Overflow, and in fact, someone last night commented that I seem to be willing to answer just about any question. Although there was a question this morning which I didn't answer because it said, how do I multiply strings in Java? And even I was stumped. I have a small software company. We've got 3 full-time developers apart from myself, and we usually engage a new client by starting with a 1-week workshop where we develop a new system, trying to incorporate best practices to within the constraints of the sort of technological decisions your company has already made as well. Moving on, my first computer was a thing called an NEC APC-1, and in fact, it went at a true 5 megahertz, as opposed to the IBM PC, which only ran at 4.77 megahertz. And it had 128 kilobytes of RAM. And I used it for many years as a teenager, first using machine code for 2 years, so that was my first language. Which, if you've read any of my Java code, that will probably make sense to you. And later used Turbo Pascal. And in all that time, I never found a good use for all 128 kilobytes of RAM. So where do microservices come from? A lot of the principles of microservices have been around for some time. Some of them are more new, but largely it's a collective term for some best practices. Now, someone mentioned to me yesterday that they'd heard that microservices come from actually in the finance area, but from the research I did, it was actually short for micro web services. Originally was the original term. So. I think in general, most people, when they talk about microservices, they think of web services, and therefore they tend to think of the sort of constraints and technologies that web services typically use. However, a lot of these principles are not specific to any given technology, and you're not necessarily limited to those technologies, and it can still be useful. Now, the reason why web services, the fact that it comes from web services, or a lot of people think of web services, is important, is that when it comes to a GUI application, there's an inherent threshold of a performance requirement, which is how fast can a human see an update? Because any update which is too fast for a human to see, it doesn't really matter how fast it is. And in fact, most movies, in fact, one of the first big films to switch from 24 frames a second to 48 frames a second was actually Lord of the Rings. So it was relatively recent that they even switched major films from 24 to 48. But you'll agree that most films which have got a 24 frame rate that you've seen, you don't see the flicker. In fact, there's actually mentioned in the Guinness Book of Records that there are people who can see the flicker because they can see changes that quick, and they find watching movies annoying. But 24 frames a second is actually 40 milliseconds. So anything that's under 40 milliseconds probably doesn't matter because a human can't tell the difference anyway. But this is like a threshold, and so it's basically we don't care about delays that accumulate to less than 40 milliseconds. Another thing about web applications is that as computers get more and more powerful, there's a tendency to make the web pages richer and richer and put more detail, more data, more information. So they tend to just grow to fit the additional processing power that your machines have. And in fact, at least according to one website, the average size of a web page is now the size of Doom, the entire game. Doom originally shipped as a 2.3 megabyte game. That was the whole thing. And in fact, the average web page is around that size as well. So every time you're watching a completely new web page, you're actually downloading the entire of Doom or something of that size. Now, I've talked about microservices in a number of banks, and we get a similar sort of reaction. Basically, the first reaction is, well, a microservices is a buzzword, and at this bank, we don't do buzzwords, which is fair enough. There's good reasons not to. The reason that I find that a bit odd is because what happens is that as they go into it a little bit more detail, they actually start to realize, wait a minute, this all sounds very familiar. We do a lot of these things already. So they've gone from, we will never do this, to actually we do a lot of this already. And then in fact, they find that they are actually doing most of these techniques already. A lot of what I actually do with clients is actually rebranding what they do already. So taking some of the techniques that they have and just relabeling them. So it is, to some degree, a marketing term. And the thing about marketing is that it's very flexible. You can actually rearrange what you have and give it a new name. But the benefit of doing this is not completely empty changes, is that this can help bring into contrast what it is that you can easily change to improve. Right? So where are the quick wins? And finally, it can help give you a direction as to where you would like to be in the medium term with a minimum of risk. That's something that's actually achievable. So this is a chart that I did recently with a client. They initially were thinking, well, microservices is not really for us, but there's a lot of drive to push us in that direction, or we need to come up with an answer for why we're not doing microservices. And then I started talking to them, well, what are you doing? And in fact, in reality, in a lot of areas, they were already doing these things. Right? So to be able to relabel themselves as microservices didn't mean they had to change everything they were doing. And in fact, that's not realistic anyway. You shouldn't be attempting to change everything you're doing. And so we just came up with a simple star rating. And we also then identified where we thought the quick wins were. So this was the initial draft. In reality, the last three were the ones that they decided they would emphasize on in the short term, which is transparent messaging, changing the structure so that teams can work more independently, and Lambda architecture. So what are the benefits of introducing techniques from microservices into trading systems? Well, one of the key drivers for trading systems is that time to market is very important. The cost of lost opportunity can be very high. So any techniques that allow you to get your solutions out faster can not only save money, but actually help the company make more money. It can make them easier to maintain as long as you're making some sensible choices. And it can also simplify your programming models. It can give you some structure and a common language to the techniques that you're using. Where microservices tends to struggle, and in fact this is something that trading systems have been doing for a long time, is how do we deal with asynchronous messaging? How do we test them? How do we profile and debug them? And in microservices, there's tend to be a lot of, well, let's base it on REST, which is synchronous typically, but you can also use WebSockets. It's sort of like, oh, and you can also do this. But really, there's not a lot of good practices around asynchronous messaging, whereas trading systems have been based on asynchronous messaging for a long time. This is generally how they actually operate. And in fact, synchronous messaging tends to be more the exception that's only really used for GUIs. Also, trading systems have a lot of techniques around how do you build deterministic and highly reproducible systems that you can test again and again and get the same results every time. Now, low latency is a term that comes up quite often, but I think it's worth trying to put some definition around it because it actually provides a bit of contrast with what most people think of when they think of web services. And that is that with low latency, the first definition should really be, the most broad definition is that you actually have a view on how much your response time costs your business. Now, what that could be different, but I've heard people talk about, oh, we need low latency, and they say, well, how much would it cost you? How much difference would you make? They don't actually have a clear idea. Really, they're just sort of like, well, users complain about latencies, we would like users to complain less. That's really the extent of the thinking. Whereas if you can have a clearer view, you've actually qualified because it really is important to you to have certain thresholds under certain, you have an SLA behind it. Now, for my purposes, low latency actually means you care about latencies you can't see. And that makes a difference because you need to have a tool set that will help you record those latencies because you cannot visually see that, oh, well, this is now going faster. Because in fact, your unacceptable latencies might be still too fast for you to see. So let me give you an example we had recently. We had an investment bank who actually refused to accept our product at one point because our 5 nines, worst 1 in 100,000, latency was 450 microseconds. That was too high for them. Now that is a latency you still cannot see. So it's the worst 1 in 100,000, but you can't see it. Now, it took us a few days of investigation to figure out what this was. Turned out it was related to parsing date times, using local date time. And after we changed the code, we managed to fix it, and we were under their requirement, which is 35 microseconds. So these are the sorts of, this is a fairly extreme example. Most of our clients aren't pushing for these kind of numbers, but it is possible to really care about latencies which, even in extreme cases, are still not appreciable to a human. So you need to have tools, and in fact, we ended up having to develop a tool just to solve this problem, which is why it took us so long. That might be a subject for another talk. It's open source, by the way, so ask me if you're interested. Okay, so one of the simplest ways to speed up a system is to do less work. If you take work out of your system, then it can run faster. And in particular, going back to the private data model of a microservice, you will get much better performance if your process will spend most of its time in its own local cache. And by staying in its own local cache, there's now less contention between different threads, and you will get better scalability because each thread now runs completely independently. Now, the caches are actually quite small. They're only 32 kilobytes for data in your L1 cache, 256 kilobytes in your L2 cache. This makes a real big difference to the performance of your application because if you access your L3 cache, then you actually can take us 10 times longer. And that factor of 10 is often more of a performance improvement than you can achieve by just putting out lots and lots of machines. So writing small services, components, single-threaded units of work that will sit on one core and not access outside the core, you can get bigger improvements in performance than just throwing lots of machines at the problem. And this tends to suit trading systems much more than it does, say, for web applications. With web applications, the main problem is throughput, not latency so much. As long as the latencies are too small for a human to see, the next biggest problem is throughput. But for trading systems, you need to minimize latency. And throwing lots of boxes at the problem actually just increases the latency. It may increase the throughput, but it also increases the latency. So in reality, you want to have a minimum of boxes, and you want to get the most out of every one of those machines. And a simple way of doing that is to have services or components that use a small amount of private data, private to them. So areas where microservices and trading systems overlap are that you want to have simple component-based design. As I said, you can still have component-based design in a monolith. There's nothing stopping you having that. But essentially, microservices will not work unless you've got clear separations of responsibility between your components, clear levels of abstraction. In a monolith, you're not really required to do that, and it's very often easy for people to put in simple solutions which actually end up causing a big web of dependencies between your components. Whereas with microservices, it just don't work if you do that. In trading systems, you do use asynchronous messaging a lot more. I believe that it's considered best practice in terms of performance with microservices, although not everyone does it. You want to have automatic and dynamic deployment of services. For performance reasons, not just for keeping responsibility simple, you want to have private data sets as much as possible. Now, an important area is what I believe is transparent messaging. Now, this is where debugging a distributed system is made so much easier if you can actually see the messages. You can actually check them yourself, because that immediately makes it easy to cut your problem in half. Is my system producing the message that's correct? Or is it producing it correctly? Or is it just that the consumer is consuming it incorrectly? And at that point, you can immediately divide your problem in half if you can read the messages. Also, from a performance point of view, your system may be behaving, working correctly, but it may be generating far more messages than it actually needs. So, for example, it's quite common for consumers to ignore duplicates. But say your producer is sending everything 3 times, right? You run your unit tests, you run all your testing, everything still works because it's ignoring all the duplicates. But as soon as you look at the message, you go, oh, everything's coming out 3 times. Right? So you can see immediately problems which may not show up in unit tests. Is it sending far more data than it needs to? Is it sending fields that never actually change, but it's sending them again and again and again with every record? You start to see optimization opportunities if you can see your messages. Okay, let's move on to Lambda architecture. So one of the models of Lambda architecture is that you have an ever-growing list of events as input to a function that is stateless, and then that has a set of outcomes for every input event. Now, this is a very simple model, and in fact, it doesn't actually work in all cases. But where it does work, you want to use this as much as possible, because these are very simple units of work, very easy to understand, and I highly encourage people to identify where in their system they can use Lambda functions and extract that work out. So then that reveals the components which have more complex life cycles. Now, as a sort of revision of this, in this model, each output is completely dependent on one message from its input. Now, there's a slight revision that I tend to take, which is, for performance reasons, is that in this case, the function is now a result of all the inputs it's ever received, right? So in theory, you could just replay every message to work out what it should do with one message, or you can maintain a state, and that state needs to be able to be completely rebuilt from all the input. Then that just becomes an optimization. So you can have some state in a Lambda function, I believe, provided it's completely reproducible from all of its inputs. Now, how do we start putting these together? Well, you might have, say, a fix engine with data coming in, market data coming in, and then you need to normalize this fixed data into an internal format. There's some fields you're not interested in, they're being sent to you, but you're not interested in them, you drop them. Some fields need to be translated, maybe some data needs to be enriched, and you produce a normalized format. So that might be your output, ever-growing messages. Then you'll have some sort of stateful component that now needs to make some decisions based on those inputs, and it may produce orders, for example. And those orders then go out to an order manager that takes your normalized order message and turns it into fix. So then the external system, the output at the other end is just fixed. Now the problem with this is your critical path. And from a performance point of view, you want your critical path to be as short as possible in terms of latency. You want it to be as quick as possible. And that means offloading work to other threads or other services. You want to be able to take work out of this critical path. Anything it doesn't need to be doing, you get something else to do it so that your end-to-end latency is as short as possible. And one way of doing that is to pass work off to an asynchronous task. Or another way of putting it is to pass it off to another Lambda function that does that work in another thread, takes the results of, say, your control system, passes it off to a strategy or an external system, or we've got one that one of these components that actually accesses a JDBC database. JDBC can take a long time, so what you would do is you would send a message out of your control system saying, I need this data. It goes passed off to an asynchronous handler. That handler then takes the results, and then it becomes the input of your control system. Now, one of the benefits of using this model is that you can replay, because everything that the system does is dependent on its inputs, you can replay all of those inputs and recreate the state of any of these components at any point during the day. And in particular, even if you're dependent on external systems, because you're capturing the results and passing through them as input, you don't actually need those external systems to be in that state or even available anymore. So say, for example, you did a JDBC query. It's passed off to a strategy, and it should be called Gateway or something. And it asks the database for some results that get passed as an input. You've now captured what result, what you knew, when you knew it, as an input. So then just replaying the inbound messages is all you need to do to recreate the state of that system at that point. And you can measure that, you can debug and test your control system completely standalone using real inputs, even with real timings, if you wish. So one of the things that I suggest people do is they work out what timing is important to them. Say maybe it's 100 microseconds. So if there's two events that are less than 100 microseconds apart, you make it a realistic gap. If it's more than 100 microseconds, then you only actually wait 100 microseconds. So that way you can replay a day's worth of data with realistic timings, but do it within less than an hour, depending on your spacing. Because you don't want to actually wait a whole day to run a whole day's worth of data. You want to be able to get your feedback quicker than that. So what do we mean by a distributed system? Generally, when people talk about distributed systems, they're thinking about multiple machines. But in reality, at the low-level timings, you actually have to think about each core as an independent processor, because you want them to run as independently as possible. You want the delay between data going from one core to another to be as efficient as possible. And in fact, within a system, you can also think of a distributed system. In particular, if you've got NUMA regions, this becomes very important, even if you're not talking about the low latency space. If you've got a JVM that crosses NUMA regions, you find your GC times just blow out fantastically. Because in reality, when you've got multiple NUMA regions, you've got actually multiple machines connected via a high-speed bus. So even though it is a high-speed bus, it's not as fast as direct memory. In reality, the OS will actually do quite a lot of work for you to make sure a process stays within one NUMA region. But certainly, if you try and create a JVM that goes across multiple NUMA regions, you will really see the difference. So as I mentioned, you want to actually model your application as a series of single-core machine processors which have their own data and can run as independently as possible. And then they communicate via the L2 coherence bus. So let's take an example. We've got, in this case, it's similar to the previous example. I've contrived this arrangement, and you'll see why. But we've still got this core routing system, which is in green. We've got market data, which is feeding data into your system. The only outputs really are data that's come from the TCP. You've got an order management system going out, and you've got a number of asynchronous processes that take a bit more time, a bit more CPU, but they're not as latency sensitive. And each one of these threads or core processes to each core have their own local data. So how does that compare to how a CPU is actually laid out? Now, across the top here, we've got 4 cores, and across the bottom, we've got another 4 cores. In between, we've got the L3 cache, which is quite a lot of silicon, but just immediately above and immediately below the L3 cache, we've got our L2 caches. I'm not sure exactly where the L1 cache is, but it could be to the left. So how does that map to our process? Well, we actually can lay out how our program will run on silicon. So now we've got, we know exactly which cores will be used for each of these individual purposes. You can use thread affinity to bind a process or a thread to an individual core. And now they just need to be able to communicate via shared memory or within the same process. And the delay between one hop and the next is actually just the speed the delay it takes to pass data from one L2 cache to another L2 cache, which is around 20 clock cycles. No, 20 nanoseconds. So you can get a very high-speed connection. Now, I haven't actually said, well, are these different threads or are these different processes? Because in reality, it doesn't matter. It should be entirely down to you to decide, do I want to run these in different processes or not? And in reality, what tends to happen is that the more stable components, it's actually easier to release them as a monolith once they become stable. They're not changing very often. I don't want to be able to release them all independently. It's just too much work. But what will tend to happen is, like, you might bring a new provider online, a new market gateway. That one is not so stable. I want to be able to restart that at any point. If it dies, I don't want it to bring down the whole system, right? I don't trust it yet. So I make it that maybe just the second market gateway is restartable. Or I make it that the strategies M to S are restartable because that trader keeps changing his mind as to what he wants. He's not too sure. He wants to be able to restart that one. So we make it restartable. But everything else can be deployed at once as a single JVM or at once as multiple JVMs. It really shouldn't matter. You should be able to design a system where your choice of how many processes you use is what makes sense for you. It's not, you shouldn't have to rewrite your code to make that happen. That's largely repeating what I just said. Okay, so one of the challenges of microservices is how do you test and debug them? Because testing and debugging distributed systems is very hard, and there isn't really very good tools in doing this. So the approach that I take is to see a microservice is actually a component, a business component, should really say business component, with a transport, and that's what makes it a service. But that transport should be optional. The transport shouldn't change the behavior of your component. And so you should be able to test your component standalone. And in fact, you should be able to test two components talking to each other without actually any transport at all. And by doing so, you now have what is essentially, for testing purposes, a monolith, or a unit testing purposes, a monolith, or for debugging purposes. But then once all your components work together and they behave correctly, you can say, right, now I want to deploy this to multiple threads, multiple machines. The components still work the same way. And so if there's any issues, it becomes because there's some sort of strange interaction between the fact that it's now asynchronous, but the actual functionality shouldn't have changed. So let's try a simple example. Say we've got a Lambda component which at the moment only has one event coming in, which is a one-sided price. So some providers for market data only give you the bids or the offers, but not both at the same time. We want to write a component that normalizes this because internally most of our providers give us top of book. We're not interested in getting individual events. That's what we want. So we have a component that takes as an input sided prices, and it produces as an output top of book prices, which have both. So our data model might look like this. We have a class called abstract marshalable, which actually implements things like toString equals hashcode, all the serialization and deserialization, but this model works regardless of whether you have that or not. So as an example, for the the toString, we actually serialize as YAML by default. The benefit of YAML over JSON is that it is designed to be human readable and it supports types. And another feature we use a lot is comments. We put a lot of comments to aid tracing. And one of the other benefits is we can take something from a log or an output and actually demarshal it and recreate that exact object. So recreating objects that come out of production are very easy, even if they're really complex. So we know that no information has been lost if it can be demarshalled. So let's have a look at this example. We have a sided price, and it goes and tries to find the relevant top of book price that would need to be updated. And then we say, if something has changed, then we trigger an event. So we have a very simple component now that can take sided prices and turn them into events which have top of book. How do we mock our component? Well, actually that's really trivial because, in fact, our component implements an interface. We can just mock the interface. Okay, so how can we test our component? Well, again, our outputs are just an interface, so we can mock the outputs. We say, these are the outputs we expect to get. Then we create our component, we feed in the inputs, and then we verify we get all the results we expected. So writing a simple unit test for this is not very complicated. Where it gets even more interesting is where you have a series of components. So the output of one, because we've used a Lambda architecture, the output of one is the input of another. So in this case, we're not only calling the combiner directly, but we can also call the auto manager. So we don't have to feed everything as input right from the start. We can take inputs to other components. Now the important thing is you can see that here that not only we can write simple unit tests, it starts up and shuts down very quickly. We can run lots of these tests. We can do a lot of data-driven testing. But this is very easy to debug, right? So after I wrote this test, there were bugs, and I used this to debug. And all I had to do was breakpoint this line. I step into here, and it steps into this code. It does something, and then steps into that code. I just go up the stack, and then I can go down the stack, and I can see all my variables. And I'm just debugging it like it's a monolith. But in reality, these are standalone components. I can put a transport between them, and now I have a microservice. So adding transports. Now, I had intended to add MPI to this list, but there's a lot of different transports that you could use, and in fact, I'm a keen advocate that you should be able to have no transport at all. So in the previous example, there's no transport. The behavior of the business logic should be the same regardless of whether there's a transport or not. Now, the one I know the most about is Chronicle Q, mostly because I wrote it. So I will spend a little bit of time talking about it. It is open source, so you can read the code. And it's Apache 2, so there's no license cost for using it. What Chronicle Q is that it's a unbounded queue. It's an unbounded persisted queue, which means that it's brokerless. It has very low latency. You can achieve less than 10 microseconds 99% of the time. It's persisted, so you can easily just copy the files from production to test and replay a whole day's worth of data for any one of those services. You can just take the inputs for that service and replay them. By recording absolutely every input that's completely recreatable, you don't need as much logging. You only really need logging for really exceptional things that you just don't expect to happen. We had one user try this. Initially, they'd implemented their trading system. They were getting 35 microseconds end-to-end, typically. And after putting in Chronicle Q, they actually realized that they were doing some redundant work. So after putting in Chronicle Q and removing the redundant work, the latencies dropped to 23 microseconds, typically. So one of the things that people ask is, well, if you're persisting everything, won't that slow you down? But in fact, our experience is by having greater transparency and better testing, is you actually speed up your application. So what does it look like? Now, this is something we've worked on quite a lot, is to make it as transparent as possible. And in fact, you can dump this out without any knowledge of the application because the messages can be decoded into YAML. So they're in a binary form for performance, but that binary can be converted to YAML for readability. I've taken out a lot of formatting to fit it onto this slide, but this is all the messages that are produced by that previous example. And you can see the header, which is sort of, it's all metadata, you don't really need to know it, but you can see that the on-order idea, which was the message that was called earlier, which is in the middle here, is called with these values. And in fact, this is what you get. Because it's a binary format, the position of the message, this is a byte offset of that message actually matters. And this is where this is a comment that comes in. So how does it form? This is done with a microserve JMH, which is a very good tool for doing micro benchmarks. One of the things it doesn't do so well is the asynchronous messaging, which is why we ended up writing our own called Java Latency Harness Benchmark. But for doing simple tests, it's very useful. And as you can see, our 4 nines is under 20 microseconds. The 5 nines is much higher, but that was actually due to the OS. I really need to upgrade my kernel. It doesn't do that on a much cleaner machine. So one of the contentious things that I think is actually quite important is that most messaging systems, again, coming from the web space, are all assuming you want flow control. And flow control is very powerful and very useful. Flow control stops your consumer from being overloaded by your producer. And as a GUI user, that's the last thing you want, because you can't be sending too much data to a GUI user because they can't see it anyway, and it's just going to slow down their machine. So it's completely pointless. However, there's lots of situations, particularly in trading systems and compliance systems, where flow control is the last thing you want. So for market data, you cannot tell the exchange, hey, I'm having trouble keeping up, can you slow down for me? It's just not going to happen. Or in compliance systems, it's usually something that other departments are told they have to have, but they don't want to be slowed down by the compliance system itself. So what Chronicle Q does is it's implemented as like a massive buffer, and then you don't need to have flow control. So it never pushes back on the producer to say, I can't keep up. The consumer may get further and further behind, but the consumer doesn't even have to be running because the queue just writes more and more to a file that grows. And then the consumer could be restarted or continue from where it's up to. And because it's all using off-heap memory, there's no problem with it running out of heap space or even main memory space. One of the things we test is what happens when the consumer is further than main memory behind the producer. We find that it actually does hurt performance, but it does continue to run. So where can I try this? We have some examples, much fuller examples of the code I just showed you on my blog repo. The actual source code to Chronicle Q and some of the other things I mentioned are on OpenHFT. And to give you a little idea as to some of the products that we have, everything in green is open source. The one that's most relevant to this talk is Q, which is a persist everything model, unbounded Q. Wire is one that's turning out to be more and more useful. It's a standard API that allows you to write to lots of different formats. And in particular, it allows you to optimize the format for a particular use case without having to change your code. So, in summary, microservices doesn't mean that you have to do everything differently. So I'm much more in favor of evolution rather than revolution. You can see it as a goal. You may decide that some of these best practices are for you, some of them are not. Most likely, the ones that are most relevant to you are the things you're already doing, but perhaps not as well as you could do. So, in fact, if you're not already a distributed system, in some sense of the word, then turning your application into a distributed system may not be the right decision. But if you are already a distributed system, such as a lot of trading systems are, they have to pass work between multiple threads, maybe there's some things in microservices that can help you improve your practices already. And yes, I'm a big fan of Lambda architecture, although I recognize that a lot of real-world applications do not fit well into it completely, but you can take work out and turn them into Lambda architecture.